Hi, welcome to my channel Too Irrational. I'm Pranay Sharma, and in this video we'll be discussing the CS1B paper conducted by IAI Institute in March 2022. We'll be discussing the solution in detail, but if you want the solution sheets, I have listed down a number in the description where you should WhatsApp or Telegram your email ID so that we will be able to email you the solutions. Let's get started. In question number 1, we can see that we have a linear style question here. Let's read. An actual student fits the following simple regression model to the data. Yi is equals to alpha plus beta xi plus ei, where I is going from 1 to 12, where ei are independent normal random variable with mean 0 and variance sigma square. The following 12 data points for x and y. Use the following 12 data points for x and y, where y is the response variable while x is the explanatory variable. So all we will do is first copy. So first thing we'll do is we'll copy and paste the codes in R Studio. I've already done that. Then let's see what they are asking us. Do not use the standard model fitting related R codes LM, GLM, fitted, residual, predict, ANOVA to answer parts of this question. They have made sure that we will be answering them using the methods of our part A. So calculate SXX, SXY and SYY. So what we'll do is we will keep the linear model regression from our formula table book, and you can refer the formula whenever you want from table book as well. Okay, so SXX, I'll say it is summation xi minus x bar whole square. Similarly SYY and SXY would be summation xi minus x bar into yi minus y bar. Using this, I'll make my SXX, that would be sum of x minus mean of x whole square. SYY similarly, and SXY would be sum of x minus mean into y minus mean. And I have taken n as our length of x. Of course, you can take length of y as well, they are the same. Then our beta would be SXY upon SXX. Alpha is going to be mean of y minus beta times mean of x. And sigma square, again refer to the table book for the formula. We'll have 1 by n minus 2 into SYY minus SXY whole square upon SXX. So we have stored all of these values. I'll just run so that you can see I have all these values here. Third part, calculate the fitted values of y using the results in part 2. So we just have to make our linear model. We have y hat is equals to alpha plus beta into x. That will give us a vector y hat that has all 12 values of the fitted values. Fourth part, calculate the residuals using results of earlier parts and calculate the mean and variance of residuals and comment on the result. So here we'll calculate our residuals. That would be y minus y hat value. Mean of a residual is nearly 0 and variance is about 10.79, which is similar to our sigma square value. It will be different because here the sigma square values are calculated by 1 by n minus 2 and here it will be calculated by 1 by n minus 1. So there will be a difference. Okay. The mean of the residuals, so we'll comment the mean of the residuals is 0 and the variance is similar to sigma square. So our assumption of normality is correct. Fifth part, calculate 95% confidence interval for beta and comment if we can conclude that the beta is not 0, stating the null and the alternate hypothesis. Calculate 95% confidence interval for sigma square. So again, these two we cannot do it from the usual R codes. We will have to use again the concepts of paper A. Note, candidates are expected to find the tabulated value using R. So we are not allowed to use the tabulated value from our formula table book. We have to calculate them. That means our T values or Z values or whatever values, we should calculate it from the R. So first of all, our beta hat minus beta upon under root of sigma hat square upon SXX, this becomes nothing but the test statistic. Degree of freedom is going to be n minus 2. Using that, we have to make a 95% confidence interval. So here, first of all, I said calculated standard deviation of beta, that would be square root of sigma square by SXX. So the 95% confidence interval, written it as a vector. We'll have beta minus QT, that becomes our T. The value that we want is 0.975 on one side. If you are taking subtraction, or you can take it as 0.025 and then say lower tail is false. And n minus 2 is our degree of freedom into standard deviation of beta. Then once I have minus, the other times I have plus, that becomes nothing but our confidence interval here. So as 0 does not lie in the confidence interval, beta is not 0. So we do have a relationship. You can write here the comment that we do see a relationship between X and Y. Okay, that should be our comment. Sixth part, state SS TOT and calculate the SS regressed, SS residual, hence calculate the proportion of variability explained by the model using SS regressed and SS residual, and comment on the result. Calculate the adjusted R square and compare it with the R square to explain the result. So first we will calculate our SS total. SS total is just SYY. SS regressed is going to be SXY square upon SXX, and SS residual would be SS total minus SS regressed. Then SS regressed by SS total is going to be 0.9371. That becomes nothing but the amount of variability explained by the model, because it is regression, sum of square of regression divided by sum of square of total. So 93.71% of the variability is explained by the model. R squared will also be exactly same, because that is how we calculate our R square. And the adjusted R square is going to adjust for the number of variables. So it becomes 1 minus R square raised to, multiplied by n minus 1 upon n minus 2. So our adjusted R square comes out to be 93.08%. Okay, so R squared shows 93.71% of the data is explained by the model. Adjusted R square adjusts R squared for the number of variables. Adjusted R squared shows 93.08% of the data is explained by the model. So this is what we can comment from the these values. You can also write that a linear model seems to be a good fit for the data. Last part, calculate the mean predicted response when X is equals to 52 and 95% confidence interval for the same. Candidates are expected to find tabulated value using R. So again, first of all, finding the response value is very easy. Y hat value for X is equals to 52. But for mean predicted response, we have to, especially for the confidence interval, we'll require the variance. So variance of our mean predicted response is here. We use this formula to find the variance. So here first X0 is 52. So our mu hat value will be nothing but alpha plus beta X0. Mu hat turns out to be 47.71. Okay, and our variance for that, exactly same formula that we just saw. And then our confidence interval, 95% confidence interval, again this value is exactly same as before. It is our quantile for T distribution with 0.975 and degree of freedom being n minus 2. So mu hat minus t value into square root of v, and same thing mu hat, it should be plus here. So here it should be plus. Let's run this from the top, and this becomes my confidence interval. I should write it as my answer. Let's go to question number 2. For question number 2, we are going to see policy data CSV, import it, these files, and we want policy data. Okay. So it seems okay. Now I always prefer to make strings as factor, although I have never seen that being a problem when we are actually using it in the R programming, but it should be factors because we always take them as factors. Import. Now this is our data: policy, claim, customer, something and amount. Okay, so let's read what the question says. So we have policy and claim information, policy data.csv of 650 policies is provided to you. The data contains the following fields: policy number, claim, a number of claims corresponding to each policy, and this is policy holders experience, so it is customer experience. We have VS, that is very satisfied, SA, that is satisfied, DS, that is disappointed, and VD, that is very disappointed. At the end of the policy tenure, the amount, that is claim amount per policy. Okay, so note that the amount is set 0 if there is no claim. Create a frequency table of claim and share how many policies did not have any claim. So we'll use the table function. So we'll have table policy data $claim. So you get the table here. You can see we have 458 policies that have 0 claims. So I have posted the table as well as 458 policies did not have any claim. And we have plot a histogram of claim count and suggest 2 distributions that can be a good fit. So we'll use histogram. You should name it properly. So the main I have written as number of claims, and X label I have written it as claims. So this is our frequency data. Okay. So looking at the data, you can clearly say that we have a discrete distribution. So we will be writing it as either a Poisson distribution or a geometric distribution because we do not have a limit to which it will be ending. The 2 suggestions I have given is Poisson distribution or geometric type 2 distribution because we need 0 as well. Given that claim count follows Poisson distribution with following 2 possible values of Poisson parameter 0.35 and 0.3, compute confidence interval at 95% confidence level to assess which value is more suitable for the given data. So here, first of all, I have taken the total claim amount or total number of claims, that is our X. Total number of policies, that is going to be N, and I have made a test, that is our Poisson.test. So Poisson.test, you can see exact Poisson test, data X and N. The number of events is 242 and the base event is, or time base, that is number of total policies is 650. So out of 650, 242 claims we see. P value is very small. Okay, and the alternative hypothesis was true event ratio is not equal to 1. Okay. So anyways, the main part is going to be our confidence interval. So we can use test $conf.int to get our confidence interval. So you can see the confidence interval is starting from 0.32 going till 0.42. So as 0.35 lies between the confidence interval and 0.3 does not, 0.35 is more suitable value. Fourth part, compute the mean, variance and median of log of claim amount. Name it log amount. You cannot keep a space when you're naming anything, so log underscore amount is what we should be keeping the name as. Make sure to exclude policies with no claims. So they have clearly said we do not want any policies with no claims. So we'll say log underscore amount would be log of policy data dollar amount such that policy data dollar amount is greater than 0. So we have made sure that it is not equal to 0. And then mean of that is going to be 9.835 and variance is going to be 0.345. Median is 9.77. Okay, median is going to be nothing but the quantile where probability is going to be 0.5. Obtain histogram and normal QQ plot of log amount. Add a line to the QQ plot for normal distribution. So we need to make histogram. So we'll say histogram of log amount. You could name, but I haven't, no problem there. Okay, I'll just run this. So here's our histogram. Okay, so it seems fairly like a normal distribution, symmetric. Okay, let's check it using QQ norm. Here we have our QQ norm plot. Seems very straightforward. We need to make a line, so we'll use QQ line. I have used color red. You can use any other color than black. Just make sure you use some color. I have taken line type as 2. So here we have our dotted line. Okay, and you can see almost all of the values are nearly the same as this line. So we might say that it is a very good normal distribution. Next part was indicate which distribution the claim amount might be following using the evidence from 4th and the 5th. Okay, so first of all, 4th, what evidence can we look for? We can look for what are the values of mean and median. And in the 5th, we can look for the histogram and normal QQ plot. So we'll say as the mean and the median are almost equal and the normal QQ plot shows that the log normal follows a normal distribution, hence the amount follows log normal distribution. Because log of amount is following normal distribution, so amount must follow a log normal distribution. Next part, assuming the log amount, that is the log of the claim amount, follows a normal distribution, test if the mean of log amount is greater than 10 at 90% confidence interval. State the hypothesis and conclusions clearly. So for the 7th part, we will have our H0 being mu equal to 10 versus H1 being mu greater than 10. I have taken my variable as y, that is log amount minus 10. Okay. So that I can directly test that mean of y is equal to 0 or greater than 0. So that is what this test is going to be. So I'll run this. Okay. And the test statistic would be this. Okay. And our p-value will be this. You can definitely write in terms of p-value. Or you can also comment it according to the confidence interval. So 90% confidence interval, you can take test to $confidence interval plus 10, because again this is confidence interval of y. If I want confidence interval of log amount, I will be adding 10 to all of the values. Okay, so if I run this, you can see this is our confidence interval. In both of the cases, you can see that 10 is a possible value. So you can say even at 10% level, we have insufficient evidence to reject H0. So mu is not greater than 10. It could be equal to or less than 10 as well. You could definitely make your test statistic and p-value like we would in paper A. That would work here too, no problem. Then 8th part, assess whether the policyholder experience, that is customer_exp, changes with more number of claims. Create contingency table and perform test to check the above assertion. State the hypothesis clearly. So contingency table For that, we can definitely use our chi-square test. First, we'll have to create a matrix to actually figure out what is going to be our total number of values in each one of these categories. So the first thing that I would test is these categories. Okay, I have four categories here, and accordingly, what would be the claim numbers that I can get? Okay, so the claim numbers we have seen before, we have 0, 1, 2, 3. Okay, so but what are the possible values we know here, but in what order do I get? So for that, I'll use table, I'll say policy data, dollar, I want customer experience. When I press Control Enter, you will see I get first DS, then SA, then VD, and then VS. This is sort of in the alphabetical order. Okay, so this is what I will be seeing whenever I am trying to make it into a matrix. Okay, so what I have done is, now I have made a matrix such that I will say, first of all, MAT is my matrix. Okay, I have made 16 spaces because for these values, and across 4 would be the number of claims. That would be 0, 1, 2, 3. Okay, these are the possible claim values. Then I have said my matrix I plus 1, that is first row, is going to be nothing but the table policy data value with the customer experience, such that the policy data claim value is going to be equal to I. My I is going from 0 to 3. That is the claim number or number of claims. Okay. Now when we run this, you will see we have a matrix. Let me show you. Okay, we have a matrix here such that for 0 claims, I have DS value as 63, SA value as 306, and so on. So this is a frequency table from this policy data according to the number of claims and this customer experience data. Okay, now we can test our chi-square test of association or contingency test, whichever you want to call it, using directly this. Okay, now the problem is that when you will do the test here, let me run the test. It is showing me a warning. It is saying the chi-square dot test MAT, okay, where chi-square approximation may be incorrect. Here they did not say that we have an error. It's a warning, so that is good enough, no problem. It has run the test. It just says there is a warning. Why is there a warning? Because there are some values that are less than 5. We know whenever we have some values that are less than 5, it is advisable to combine them with the previous value. Okay, so we have not done that, no problem. Okay, because that is actually one of the questions later on. So test.set our test statistic is going to be 47.748. P value is going to be almost negligible. Okay, e raised to minus 7. So as the p value is very small, we have sufficient evidence to reject H0. Policyholder experience changes with number of claims. Okay, I have written my H0 and H1 as well. H0 will always be that they are independent, and H1 will be that they are dependent, right? Here they are saying, please explain why warning message appears while performing the above test. So we are saying as some values are less than 5, we see the warning message. Okay, so because the number certain values are less than 5, we are getting some warning that it may not be accurate. Okay, or approximation may be incorrect. 10 part, again perform the above test by combining, first of all, very satisfied and satisfied customer, then disappointed and very disappointed customer, and 2 or more claims. So we'll have 0, 1, 2 or more claims, that is 2 and 3 we have to combine. So our last row and second last row we need to combine. And then very satisfied, satisfied, and disappointed and very disappointed. So again here the order matters. I want to combine DS and VD. So first column and third column I need to combine, and second column and the fourth column I need to combine. Okay, so that is what I have done here. In the same matrix, I said my second column must be nothing but the second column plus the fourth column, and the first column must be first column plus the third column, and the third row must be the third row plus the fourth row. Then I have made a new matrix that chooses only first and the second column and only the first three rows out of this matrix. So MAT, choose only the first three rows and only the first two columns. Now let me run this. Okay, and you can see MAT2. Okay, matrix 2, here we have, you can see now we have only two columns. One of them, first column is DS plus VD, you can see, okay, and SA plus VS would be our second column. Okay, so dissatisfied and satisfied customers. Then we have 0 claims, 1 claim, and 2 and more claims here. Now after combining these, you can see clearly that none of these values are none of these values are less than 5. So we will not see this warning message. Now let's run the same test here. You can see we do not get any warning message because all values are greater than 5. Okay. P-value. So test statistic value is 43.5. P-value is still very small. So same thing, as the P-value is very small, we have sufficient evidence to reject H0. Policyholder experience changes with the number of claims. So the last part, amount is defined to be large if the amount is greater than 100,000. 95, calculate the 95% confidence interval for proportion of large claim and comment on the likelihood if more than 25% of claims are large. So here I have run the amount separately. So I'll say amount is going to be policy data dollar amount. Then large claims would be amount such that amount is greater than 100,000. Okay, and the 95% confidence interval, we'll calculate the quantile from these large claims for the values 0.025 and 0.975. So we get our confidence interval is being this. Now they wanted to know how many what is the percentage or likelihood or the percentage of our large claims out of the total claims. Now first of all, they have defined this at the beginning that, where is question number 2? Here note that the amount is set to 0 if there is no claim. So we do not want those values where we have no claim. We want where we do have claims. We are going to ignore the values with amount 0. So therefore, to check how many of the total claim values are large claims, I'll say length of large claims divided by length of total claims. That would be amount such that amount is greater than 0. So we get about 18.22% or 18.23%. 18.23% of the claims are large claims. Let's go to the next question. For question number 3, a general insurance company is trying to analyze the two-wheeler motor insurance claim reported over last 1 quarter. The data is provided here with the file motor claims.csv, which contains the following field. We have policy number and claim, that is the amount of claim reported for the policy. Okay, so first of all, let's load it. Motor claims. Seems okay. Import. Okay, so we have policy and we have claims. Insurance company is interested to find out an appropriate distribution to fit the claim data. You are being asked to find out the appropriateness of the following distribution based on the method of movement. So we have normal distribution, log normal, exponential, and gamma distribution. Normal distribution, very straightforward. We'll just compare mu and sigma with the mean and the standard deviation. But for log normal, at least I had to figure out what our MME is going to be. For our method of movement, we'll say our expected value must be equal to x bar. For log normal distribution, that would be e raised to mu plus half sigma square. Variance is s square, that would be e raised to 2 mu plus sigma square e raised to sigma square minus 1. So we get s square by x bar will be equal to e raised to sigma square minus 1. So sigma square would be log of s square by x bar plus 1. We'll substitute that for our mu. So we'll get mu is equals to log of x bar minus half of sigma square. Okay. So using both of these formula, we will now create the parameters for log normal distribution as well. Keep parameter as mu and sigma, not sigma square, because we will be using sigma as our parameter in R programming. So first of all, I've written claim as our motor claim, dollar claim. Okay. Taken x bar as the mean of the claim and s as the standard deviation so that we can use it directly. Normal distribution, I have said the parameters are going to be mu comma sigma. So mu is going to be our x bar, sigma is going to be s. Straightforward. Log normal distribution, I have taken mu L and sigma L as the parameters. We just wrote the formula for both of them. So I have just written it here. Exponential distribution, we know our lambda for exponential distribution is going to be 1 by the x bar. Here we go. And gamma distribution, I have taken a comma b, where b is going to be our x bar by s square and a is going to be b into x bar. Okay, so here we have all of the parameters of these four distributions. Then second part, plot a histogram of claim data with 35 equal class intervals. Superimpose the histogram with the probability density function of the above four distribution using their estimated parameters as obtained in part 1. Mark each plot distinctly using appropriate legends. So for histogram, first thing I did was I just said HIST claim to figure out what are the possible values here, because we want 35 equal divisions. So for that, first we need to know how many divisions, how many total values do we have. So you can see we are starting from 0 going till about 55,000, right? We are going till 55,000. So that would be our limit. So the breaks that we will be setting is going to be our vector 0 to 55,000, where length dot out is going to be 35. Probability true, because we want to now superimpose the densities. Okay, you can definitely change the names and stuff. I was okay with the histogram of claims and claims being here, no problem there. Okay, so now we will see the histogram with 35 divisions. Okay, here we have 35 divisions. Now we need to superimpose our densities of each one of these distributions. So first of all, I'm using lines function. You can definitely use curves function as well, no problem. I'm setting my x to be 0 to 55,000 and changing by 100 so that I have very small values. Rather, I have a total of 551 points where these lines will make. Okay, then make sure that each one of these lines are of different colors. So I have taken normal distribution with blue, log normal with red, exponential with green, and gamma with yellow. You can choose any colors, just make sure they are different. Then we'll say our line will be x and d, whatever distribution we are talking about, x comma the parameters, and then the color. You can definitely change line type, width, whatever you want. This I find the easiest. For all four, I will run them and we'll see the 4 lines, right? So you can see that the most likely a distribution is going to be a log normal distribution, or maybe the yellow seems to be also very close to the graph. So maybe gamma distribution or the log normal distribution. We also want legend. So for legend, I have created a name because these are the 4 names in that sequence, and also the colors. So normal for blue, log normal red, exponential green, and gamma yellow. So I will run this. And I'll say legend should be on the top right. So x is equals to top right, and legend would be the names, and the color would be the color, and the line type I want 1 because I have made all line type 1. If you have made different line types, you will have to specify it as a vector here as well. We'll press Ctrl Enter, and here we have the legend. Okay, so it's always better to make the correct form of the diagram or how much you want space here, and then make the legend. So I will run this, Ctrl Enter, and this looks good enough, and then I will copy this in the Word. Next is compute the 5% 5th percentile, first quartile, that would be 25%, median, that is 50%, third quartile 75%, and 95th percentile of both the actual claim paid as well as the fitted distribution. So for all distributions, we'll have to create the percentiles or the quantiles. So I have taken all the values: 5th percentile, 95th percentile, first quartile, median, and second quartile values as a vector. Then for the actual claim paid, it will be quantile, claims, comma, values. Here we get each one of them. For normal distribution, Q norm, values, and then give the correct mean and the parameters. Same thing for each one of them. Okay, so that is what I have done here. For each one of these distribution, we have all the correct quantiles. Now we have to compare. I think for the next part, we have to compare and see which one is the closest. Okay, so using the result from 2 and 3, comment on the goodness of fit of the models to the data. So again, from 2, that is our graph. You can say that log normal or the gamma distribution seems to be a good fit. Okay, so from the graph, the closest fit seems to be log normal or the gamma distribution. Now I can even check here which one is the closest. So if you see the actual quantile value I had for 5%, 1324. Normal is very far away, log normal, okay, near, exponential far away, gamma is also far away. But for the later on values, 1934, I have 2300, and for gamma, you can see it is 1400. Then 3631, I have 4200, and here I have 4053. Here for 7000 something, and here I have 8000. So these are very near values to the actual values. So what I have done is calculated the differences. So for the quantile claim value, that is this actual paid minus the log normal value and the gamma value. These are the differences from each one of them, and you can see now you can directly compare the differences clearly. For the first, second, and the fourth value, the log normal is definitely closer, but for the third and the last value, our gamma distribution is closer. Okay, so you might say both are nearly the same. So accordingly, I have written here, from third, the closest value in the most quantiles is of log normal distribution. Looking at part 2 and 3, we can see that log normal distribution will be the best fit. You can also comment that second best would be gamma distribution, or you can say gamma distribution will also be a good fit. Then next, assuming gamma distribution to be the right fit to the data, simulate 20,000 values of the claim amount using the gamma distribution based on the parameter estimates obtained in part 1, and print the first 10 values of the claim amounts. Set.seed 2022. So we'll say set.seed sample, we have R gamma, 20,000 values and the parameters, and we want to show the first 10 values. So I have set sample first to 10. So these are the first 10 values. Next, generate 700 different random samples of size 400 from the simulated data obtained in part 5 and compute the sample mean of each of those samples. Set seed to 2022. So again, set.seed, and now we have to create 700 samples. So we'll use for loop. For loop, x will be equal to nothing but the sample from this SAM. Okay, that is created sample here. We want of size 400 and we want the replace to be true. Then we have to create x bar, and I am storing it in the x bar ith value. Okay, so we'll run this. So I have 700 x bar values here. Plot the histogram of sample mean and generated from part 6th, and comment on the distribution of the sample mean from the point of view of the central limit theorem. So we know that it is most likely going to be a normal distribution. Okay, so we will create the histogram. Here we have histogram. It seems fairly symmetric, okay, and normally distributed, like increasing and decreasing bell curve. So that is what I have written here. The graph seems fairly symmetric and seems to follow normal distribution. The central limit theorem seems valid. Overall, the paper was lengthy, but it was simple. Okay, it was definitely achievable in 2 hours. It might be a little bit confusing in some parts, but overall the paper was very straightforward. If you find any mistake, leave them in the comments. I will make sure to pin them so that others can see them too. Do like, share and subscribe, and I will see you in the next one.